So in this section, we're going to talk about nearly circular orbits and central fields. Again, not necessarily 1 over r squared field, but just a central field. And then we're going to talk about the stability of the orbit. We're going to make we're going to draw some conclusions about that. I'm going to start with the radial force equation. Remember, we started with a vector force equation. We broke it into a radial part and an angular part using polar coordinates. And this was the radial part. And we did a little work early in the chapter and showed that theta dot was the angular momentum per unit mass divided by r squared. And so this equation becomes mr double dot minus m, and so it's r times this thing squared, which ends up being L squared over r cubed equals f of r, right? And since this is the acceleration in the radial direction, right, we get r double dot equals 0. The radius is not changing, and so r double dot equals 0 for a circular orbit. And so, you know, so for r equals a, we get, we get this equation for a circular orbit. Ml squared over a cubed is equal to f of a. And if this was a gravity force, we could end up with a relationship between the period and the radius by breaking that equation down further. But now let's suppose a nearly so we could say like r equals a plus x, where x is maybe much less than a, and so the radius is mostly circular, but it's got some slight variation from circular, and so we could write this as x equals r minus a if we wanted to, right? X is the difference between whatever the radius is and the circular orbit that it would be if it was just a little more perfect, right? And so if we do that, then this equation, so like this equation becomes m r double dot minus m L squared over r cubed equals f of r, right, becomes m x double dot, right? R is x plus a, but a has no time derivative, and so mr double dot just becomes mx double dot minus m L squared over x plus a cubed equals f of x plus a. Right. And so now we can take this these two terms and do a series expansion on them. We can do a Taylor series on this guy, or a binomial series on this guy, which is the same as a Taylor series, really, and just keep the first two terms as long as again x is much less than a, right? And we can learn something from those equations. So this is the form of the equation with written with a plus x instead of r. And so I'm going to do a Taylor series expansion. This is again nearly circular orbits and central fields. Here's my radial force equation. I'm taking nearly circular orbits, and so I'm going to replace r with a plus x, where x is, a is a constant, maybe the average radius or something like that, and x is something slightly off of that, right? X is the variation from circular, and hopefully it's very small for these examples, right? And so what we're going to do is we're going to do series expansions on these two guys, and just keep the first two terms. And so just the definition of a Taylor series, f of a plus x, right? It's just f of a plus f prime of a times x plus f double prime of a times x squared over 2 factorial plus dot dot dot. Again, we're just going to keep the first two terms of that. Similarly, I'll just look at the ml squared is constant, so I'll just say, look, 1 over, let me move it over a little bit, right? 1 over a plus x cubed. You can just use this formulation, right? It's 1 over a cubed plus the first derivative, which is minus 3 times a plus x, so minus 4 times x. No, it isn't. It's minus 3 times a to the minus 4 times x plus f double prime of a again, and so it's minus 4 times minus 3 times a to the minus 5 times x squared over 2 factorial plus dot dot dot. And again, we're only going to keep the first two terms, and so my differential equation from the top looks like this. It's mx double dot equals, and so this is ml squared times the first two terms of this, which is 1 over a cubed minus 3x over a to the fourth. Right, that's what that one becomes. And then it's plus the first two terms of this, which is f of a plus f prime of a times x. Right. And if you remember from the last screen, we said that for a circular orbit, f of a is equal to minus m l squared over a cubed. Right? That's what happened to this equation when x double dot was 0, right? And you know, in this case, in the discussion, x would be 0 since it's a circular orbit. And so this term is just minus ml squared over a cubed, which would cancel with this term. And so we would get that and that go away. And now we would have a fairly small equation with the right-hand side just depending on x. And so I'm just going to write that up here. Right? And so this becomes mx double dot equals, and so it's minus m l squared times 3x, so I put the minus sign on the outside, over a to the fourth, and then it's plus f prime of a times x, right, plus that term. So it's these two guys and that one. Again, I'm going to recognize that minus ml squared over a cubed is f of a, and so this gives me mx double dot equals, and so this is f of a over a times 3x plus f prime of a, or times x, which is f of a over a plus f, try again, 3 f of a over a plus f prime of a times x. And so mx double dot, if I want to, I can say minus 3 over a f of a minus f prime of a plus, times x equals 0. Does this look like anything to you? Does this look like a simple harmonic oscillator problem? Right? This is just something times the second derivative minus some constant times the second derivative minus some constant times the first derivative is 0, right? Or if I wanted to, I could write mx double dot plus minus 3 over a f of a minus f prime of a x equals 0. I could divide through by m's. This is a simple harmonic oscillator problem. Provided the term in brackets is positive. right? And so what that means is if it's slightly off, it'll oscillate about the equilibrium position, provided that the term in brackets is positive. So if the term in brackets is greater than 0, I get a simple harmonic oscillator type behavior. If the term in brackets is less than 0, then I get an equation that looks like this, where k is positive. And the solutions to that is, rather than sines and cosines, which it would be for this, it's an exponential. And you can just check this if you plug in this function. If I just take this piece of it, the second derivative of that is k a1 e to the square root of kt. And so that's what the second derivative looked like. And I'm subtracting the same quantity, and I get 0. So either of these forms a solution. So the solution is some combination of these. And notice it says that as time increases, x is increasing exponentially, potentially. And so the orbit's unstable. So these are arguments for stability. If the term in brackets is greater than 0, the orbit's stable. If the term in brackets is less than 0, the orbit's unstable. And so then we can say, well, I can just look at an orbital behavior. Suppose is equal to suppose my force function is minus k times r to some power, right? And so, this is gmm over r squared. But I can just look and say, well, what values of n are give me a stable orbit? And it's those values where this function is greater than 0. So I can say, well, so f of a is equal to minus k a to the n, right? And then f prime of r is equal to minus k n r to the n minus 1. And so f prime of a is equal to minus k n a to the n minus 1. And so then I can look at this term, right? Minus 3 over a times f of a, which is minus k a to the n, right? And then minus f prime of a, which is this guy, minus k n a to the n minus 1 is greater than 0, right? And so what I get here is this becomes 3k is positive a to the n minus 1 plus k n a to the n minus 1 is greater than 0. That means 3k plus kn is greater than 0. Let me just go back up to the top. Right. I'll just start with this equation. I'm just substituting into that equation, solving. This becomes 3k a to the n minus 1 plus kn a to the n minus 1 has to be greater than 0, right? Well, a is just my orbital radius. It's positive, right? And so a positive number to any power is going to be positive, and so I can chunk those guys. I can just divide them out, and that means that 3k plus kn is greater than 0. So 3 plus n times k is greater than 0. But we're assuming k is my GMM term. We're assuming k is greater than 0, and so that just says 3 n is greater than minus 3. And so in order to have a stable orbit, my r to the n power has to be greater than minus 3. And so minus 2.9 would work, but that's why we get nearly circular orbits in one of our squared forces that are stable. Like the Earth's orbit.